This video will cover inequalities, including representation on number lines and solving linear inequalities. We will explore representing inequalities on number lines, solving linear and quadratic inequalities, and inequalities with regions and two variables. An inequality is an algebraic statement using symbols like greater than, less than, greater than or equal to, and less than or equal to. Two inequalities can be combined into a single statement, like 3 is less than x, which is less than or equal to 14. Inequalities can be read from left to right or right to left. For example, 5 is greater than -3 is equivalent to -3 is less than 5. In general, x is greater than y is equivalent to y is less than x, and x is greater than or equal to y is equivalent to y is less than or equal to x. To represent inequalities like x is greater than 2, we use a number line. Because there are infinitely many solutions, we use a hollow circle at 2 to show it's not included, and an arrow extending to the right, showing the solution set. The set of values that solve an inequality is called the solution set. To represent x is less than or equal to 3 on a number line, we use a solid circle at 3, because this number is included in the solution set. An arrow extends to the left, indicating that the solution set continues indefinitely in that direction. For a compound inequality like -1 is less than or equal to x, which is less than 4, we use a solid circle at -1 since it is included. A hollow circle is used at 4, as it is not included. The line segment between them represents all the values in the solution set. Now, let's practice writing inequalities from number lines. This scene is an interactive activity for practicing representing inequalities on number lines. For integer solutions, x can only be a positive or negative whole number. For the inequality, -3 is less than x, which is less than or equal to 5, the integer values that satisfy this are -2, -1, 0, 1, 2, 3, 4, and 5. To find an inequality for the integer set -4, -3, -2, -1, 0, 1, there are 4 possible inequalities. These range from -5 is less than x, which is less than 2, to -4 is less than or equal to x, which is less than or equal to 1. Remember that less than or greater than signs mean the end values are not included. We are now moving on to the section covering solving linear inequalities. To solve x plus 3 is greater than or equal to 7, we subtract 3 from both sides, which gives x is greater than or equal to 4. The solution has the letter on one side of the inequality sign and the number on the other. Similar to equations, we can solve inequalities by adding or subtracting the same value to both sides, or by multiplying or dividing by a positive value. For example, to solve for x, -7 is greater than 11 minus 2x, we add 7 to both sides, giving 4x is greater than 18 minus 2x. Then add 2x to both sides, giving 6x is greater than 18. Dividing both sides by 6 gives x is greater than 3. To check the solution, x is greater than 3, we substitute a value just above 3, like 4, and a value just below 3, like 2. Substituting 4 gives 9 is greater than 3, which is true. Substituting 2 gives 1 is greater than 7, which is not true. This confirms the solution. Most inequalities can be solved like equations, but we must be careful when multiplying or dividing by a negative value. If the simple inequality -3 is less than 5 is multiplied by -1, we get 3 is less than -5, which is false. To keep the inequality true, we reverse the sign to get 3 is greater than -5. Remember, when both sides of an inequality are multiplied or divided by a negative number, the inequality sign is reversed. For example, to solve 4 minus 3x is less than or equal to 10, subtract 4, then divide by -3. The sign reverses, giving x is greater than or equal to -2. Alternatively, move the x terms to the right side, giving the same result. We can write two separate inequalities as a single combined inequality, such as 5 is less than or equal to 4x plus 3, which is less than 15. To solve this, subtract 3 from all parts, resulting in 2 is less than or equal to 4x, which is less than 12. Then, divide all parts by 4 to get 0.5 is less than or equal to x, which is less than 3. This solution can be illustrated on a number line. Some combined inequalities contain variables in more than one part, like x minus 2 is less than or equal to 3x plus 2, which is less than or equal to 2x plus 7. Treat this as two separate inequalities. The first gives -2 is less than or equal to x. The second gives x is less than or equal to 5. The complete solution is -2 is less than or equal to x, which is less than or equal to 5, shown on the number line. To solve 2x minus 1 is less than or equal to x plus 2, which is less than 7, treat it as two separate inequalities. The first gives x is less than or equal to 3, and the second gives x is less than 5. If x is less than 5, it is also less than or equal to 3. Thus, the whole solution set is x is less than or equal to 3, as shown on the number line. To solve 4x plus 5 is less than 3x plus 5, which is less than or equal to 4x plus 3, treat it as two separate inequalities. The first gives x is less than 0, and the second gives 2 is less than or equal to x. The solution has two parts and cannot be written as a single combined inequality. The solutions are x is less than 0 or x is greater than or equal to 2. This is illustrated on the number line. We are now moving on to the section covering inequalities and regions, including vertical and horizontal regions. Inequalities can be represented by regions on a graph, which is an area where all points obey a given rule. For the inequality x is greater than 2, we seek the area where every point's x coordinate is greater than 2. Points like 4, 1, 6, 5, and 3, -2 satisfy this. The line x equals 2 represents all points where the x coordinate is 2. For x is greater than 2, the line is dotted because points on the line are not included. The shaded region to the right of the line shows where x is greater than 2, while the unshaded region to the left shows where x is less than 2. This scene is an interactive activity for practicing various vertical regions based on inequalities involving x. This scene demonstrates the effect of combining more than one region involving x based on compound inequalities. Now let's explore horizontal regions. Suppose we want to find the region where y is less than or equal to 3. This means the y coordinate of every point must be less than or equal to 3. Examples include 5, 1, -3, -4, and 0, 2. The line y equals 3 represents all points with a y coordinate of 3. For the inequality y is less than or equal to 3, the line y equals 3 is solid because points on the line are included. The shaded region below the line y equals 3 contains every point where y is less than or equal to 3. The region above the line contains every point where y is greater than or equal to 3. This scene is an interactive activity for practicing various horizontal regions based on inequalities involving y. This scene demonstrates the effect of combining more than one region involving y based on compound inequalities. When several regions are shown on the same graph, we usually shade out the unwanted regions. This helps easily identify the required area where regions overlap. For example, to show the region where -4 is less than x, which is less than -1, and -1 is less than y, which is less than or equal to 3, we shade out the unwanted regions outside these ranges. This scene is an interactive activity for practicing combining vertical and horizontal regions based on compound inequalities. We are now moving on to the section covering inequalities in two variables. Linear inequalities can involve two variables, x and y, such as x plus y is less than 3. The solution set consists of pairs of values like 1, 1, 4, -5, and -1, 0. These solutions can be represented graphically as coordinate pairs. We represent points where x plus y equals 3 with the line x plus y equals 3. Since x plus y is less than 3, the line is dotted, indicating that points on the line are not included. The region below this line represents x plus y is less than 3, and the region above represents x plus y is greater than 3. For a sloping line, it may not be obvious which side contains the required region. We can check by substituting a test point, usually the origin, 0, 0, into the inequality. If the point satisfies the inequality, it is in the region. Otherwise, it is not. To determine if 0, 0 is in the region for 4y minus 3x is greater than 2, we substitute x equals 0 and y equals 0. This gives 0 is greater than 2, which is false. Therefore, the region representing the inequality does not contain the origin. This scene is an interactive activity for practicing shading regions based on inequalities in two variables. This activity demonstrates the effect of combining two inequalities with two variables. This activity demonstrates the effect of combining three inequalities with two variables. In real-life problems, inequalities help model constraints. For a ferry that cannot hold more than 30 tons, with X cars weighing 1 ton and Y lorries weighing 3 tons. The inequality is X plus 3Y is less than or equal to 30. If 20 cars are on board, solving for Y shows the ferry can carry a maximum of 3 more lorries. To graph the possible numbers of cars and lorries, we draw the line X plus 3Y equals 30 within the axes range of 0 to 30 for X and 0 to 10 for Y. The points on the graph represent the solution set, which is a finite set of points because the number of vehicles must be whole, positive numbers. We are now moving on to the final section of this video, covering quadratic inequalities. Quadratic inequalities often have 2 solutions. For x squared is less than 4, we consider both positive x squared is less than 4 and negative x squared is less than 4. Taking the square root gives x is less than 2, and also x is greater than minus 2. These solutions combine to minus 2 is less than x, which is less than 2. For x squared is greater than 4, the separate inequalities are x is greater than 2 or minus x is greater than 2. Multiplying the second by minus 1 and reversing the sign gives x is less than minus 2. Thus, the solution is in 2 parts. X is less than minus 2 or x is greater than 2. This is shown on the number line.